So when I'm working a projectile motion problem, I know I want to start basically the same way I did with any other kinematics problem. I'm going to start by taking the information I'm given and I'm going to draw a couple of pictures, one showing the initial situation, one showing the final situation. So the initial situation is obviously right after the projectile has been launched. The final situation is right before the projectile lands. In this case, let's assume that we're standing on top of some building or cliff and we're going to throw our projectile horizontally. So I have an initial velocity vector that points horizontally. I know that projectile is going to fly out and hit the ground traveling with some velocity that points downward. It's going to have picked up speed, so the final velocity vector will be larger in magnitude than the initial velocity vector. I know that the acceleration vector over its entire motion is going to point straight down. And then I can also pick a coordinate system. And so in this case, I'll put the origin at the base of the building where I'm releasing my projectile from. And then that lets me draw in initial and final position vectors. And so just like we would with any other kinematics problems, we can start by drawing out the 5 vectors that we know that we're going to care about in terms of setting up our problem and figuring out what equation that we want to use. Since I've picked my coordinate system, I can go through and break all 5 of these vectors up into their components. So here again I recognize that the acceleration has an x component of 0, its y component, given my particular choice of coordinate system here saying positive y points up, the acceleration is going to have a y component that's negative. My 2 velocity vectors, I can redraw them from the same axis, break those up into components. What I notice, of course, is that the x components are going to be the same. For the initial velocity vector, it's entirely in x. For the final velocity vector, it has that same x component, but it now also has this additional y component pointing downward. And then with the initial and final position vectors, the initial position vector points straight up, the final position vector points to the right, so I know that all of the initial position is going to be in the positive y component, all of the final position is going to be in positive x. So I can take that information and put it into my table. In general, I'm always going to end up with the same acceleration for a projectile motion problem. X component's always going to be 0. The y component's always going to be plus or minus 9.8 meters per second squared, and that's known simply by the virtue of knowing that my object travels like a projectile. I can break up the rest of those vectors depending on what the various parameters are of my problem. But the other detail I want to keep in mind is that I know that the x components of the initial and final velocity vectors, those have to be the same because I know that I have constant velocity motion in x. I also know that time is scalar, but that the projectile is going to travel the same amount of time horizontally as it is vertically. So again, this isn't the x and y component of time because time's a scalar, but I'm going to use the same value for time to describe both the horizontal and vertical motion. Now there are some special cases, and again this is just sort of in some sense translating the information I'm being told in the problem. So if I have a situation where I'm told that my object is thrown horizontally or maybe it's dropped, then I know that the initial vertical component of the velocity is going to be 0. If it's at its highest point, whichever point in time that is, then the y component of the velocity is also going to be 0. If I have an object that's thrown straight up or dropped or thrown straight down, those are one-dimensional problems. It's just traveling vertically, and so all of the x components are going to be 0. And so once I've set up my table figuring out what I know within the problem, again I can think about my questions in terms of figuring out which equations I want to use. Is the acceleration of the object 0? Well, yes, in the x direction, which means that the horizontal motion of the projectile is described by a single equation. So the final position is equal to the initial position plus the horizontal velocity times time. The acceleration is not 0 in the y direction, but I do know that it is constant, so that means I've got my 3 constant acceleration equations. And again, if I know time or want to know time, that's probably going to take me towards my 2 time equations. But if I don't know time or think I can get away without knowing time, then I want to use that v squared equation, just like always. One of the things to keep in mind is that this v squared equation, again, if you're solving, typically it'll be for the final velocity, but this is also true for the initial velocity if that happens to be what you're solving for. You're responsible when you take the square root to solve for either of those two quantities of knowing whether you want the positive or negative root. And again, that's really a function of, do you know what's going on with enough certainty at the instant in time that you're talking about to know whether your object is traveling up or down, and then which direction did you pick to be the positive y direction. So you're responsible, if you end up using that equation to take the square root, for making sure that you get the right sign with either of those two components. If, on the other hand, you use time, then it becomes back to, well, what do I know more about? Do I know more about the positions or the velocities? If I know more about the positions, then I have my position as a function of time for the vertical motion. If I know more about velocities, then I have my equation describing the velocity as a function of time for the vertical motion.